Okay, anybody have any homework questions you want me to go over? Well, it's a little hard to keep all this stuff straight, so let's think back on what we're talking about here. So first we talked about the different types of forces. And those were broken up into, the first category was the weight. And the second category was contact forces. And I broke contact forces up into 3 separate force types. The first one was pushing. The second one was pulling. And the third one was friction. And we went through a bunch of free body diagrams using, for these different types of forces. And then we started doing calculations with Newton's second law. And we did Newton's second law on single bodies. And then we started talking about the 3 specific problem types and how to approach those. So 3 types of problems that kind of require a particular way of approaching these things. The first one was collections of bodies with the same accelerations. And remember that to solve problems like this, the first thing we did was isolate the whole system as a single thing. And we used that to calculate the acceleration. And then we isolated individual bodies. So we're done with this one. Now we're going on to 2 new ones. And today we're just going to do the second one. This is rolling and sliding problems on inclines. So for the first time, we're going to start doing things that are rolling or sliding on ramps that are at an angle. And then the last thing we're going to get to next class, not today, is collections of bodies with different accelerations. And when you get to this, it's all going to be involving cables and pulleys. Okay, so last time we talked about collections of bodies with the same acceleration. Now we're going to get to rolling and sliding on inclines. And this is the first place in this class where we're going to choose a coordinate system that doesn't have y pointing up and x pointing to the side. Okay, so we're going to use a new coordinate system orientation in these problems. So if you have a problem like this, the coordinate system is going to have the y-axis pointing straight out of the surface and the x-axis pointing along the surface. like this. Once you choose the y-axis pointing out of the surface, we're always going to have, it's always going to be just rotated versions of our usual coordinate system. So this is the direction that x has to point. And if you have a ramp that's oriented the other way, again, we're going to choose the y-axis pointing out of the surface. In this case, since this is a rotated version of the usual coordinate system, the x-axis has to be up the ramp. So we're always going to choose the y-axis straight out of the surface. And that means that the x-axis always is along the surface, parallel to the surface. Why are we going to do this? Well, these problems are perfectly possible to solve without using this funny coordinate system. But it's worth noticing that we're just going to do this because it makes things easier for us. So this is going to make the math easier. Okay, so I'm going to try to help you understand how this makes the math easier. So we'll list out sort of a cost-benefit analysis, benefits over here, drawbacks over here. Okay, so think about this cart on the left over here, okay? If we used a normal coordinate system for that, the usual coordinate system for that, notice that this thing would be moving along an axis that wasn't the x or y axis. It would be at an angle, okay? So you'd have to use cosine and sine to represent that acceleration. It's not that it's impossible, but it's a pain, okay? And so the first benefit is that with this rotated coordinate system, the acceleration vector, we can just represent it as a0. Okay, if we used a standard coordinate system, that isn't how that would look. Okay. Second, remember that the normal force, the pushing force from the ground, is toward the chosen body, perpendicular to the surface. Well, again, since the ground is at an angle, that normal force would be, we'd have to use cosine and sine to figure out what the components of that force are. But with this rotated coordinate system, this is just going to be 0, positive n. Okay. And then the friction force in problems where there's friction, that's going to be always parallel to the surface. With the rotated coordinate system, that means it's going to be either in the positive or negative x direction. So the friction force is going to be plus or minus the coefficient of friction times the normal in the x direction and 0 in the y direction. Okay, so all of these would be sort of complicated combinations of cosine and sine. It would be a pain. It's possible, but it's just a lot more work. It's a lot easier in this case. There is one drawback though. Okay, I mean, it's 3 benefits to 1 drawback, so you see why we're doing this. But the one drawback is that the weight force, if you use the standard coordinate system, is always really simple, right? It just acts in the negative y direction. But now this is going to be mg times the cosine and sine of some angle. So I'm going to write this as mg times the cosine of some angle phi, mg times the sine of some angle phi. Okay. So these are all simpler in the rotated coordinate system. This one is messier in the rotated coordinate system. Okay. Anybody have any questions about? So this hopefully convinces you, like, okay, this is worth doing, you know, like we don't want to think about all these angles. We'll just instead think about this one angle. Okay. So let's think about that weight force. Okay. Let's say that this angle is theta for the ramp. And here is our mass. The weight force is like this. Okay. The coordinate system is oriented like this. And so what I want you to notice is that this angle is theta. Okay? So the angle of the ramp with the horizontal is how much the weight force deviates from 270 degrees. (270 degrees being the negative y-axis. Okay, so if this angle is 20 degrees, then think back to the vectors daily problems that you did. In order to calculate the components of this vector, you'd go mg times cosine of the angle from the positive x-axis to the vector, right? In this case, that would be 20 degrees short of 270, so this would be 250 degrees. Okay, if that ramp was pointed the other way, it would be 20 degrees past 270, so it would be 290 degrees. And so whichever way this ramp goes, and I'll draw the other one too, the other possibility. So let's say this time this is the angle theta. And this is the weight force. The coordinate system is this. And so this angle is theta. Okay, so you're always going to, whatever that angle is that the ramp is at, it's always going to be, for the weight force, 270 minus that or 270 plus that. Okay, and you've done this kind of problems before, figuring out this angle. It's just like those vector problems you did. Okay, so let's just get into some problems and you'll see how this works. Okay, so let's say you have a 20-degree angle and a cart like this. And let's say this cart has a mass of 10 kilograms. And we want to know what's the acceleration vector of the cart. We're going to use a coordinate system with the y-axis pointing straight out of the surface. So x is pointing that way. I'll draw a free body diagram. So we have a weight force down here of 10 times 9.81, so that's 98.1. And now go around the boundary looking for contact with the surroundings. There's only one place the surroundings contact this boundary, and that's at the wheels. And that's a pushing force. I'll call that N. And now we have to think about the components of that weight force. So here's the coordinate system. Here's the weight force. We know that this angle from the negative y-axis to the vector is 20 degrees, because that's always the same as the angle of the ramp. And the magnitude of this is 98.1. So that weight force is 98.1 times the cosine of, okay, what's the counterclockwise angle from the positive x-axis to this vector? Is it, I said that it's always going to deviate from 270 by this amount 20. So is it going to be 250 or 290 in this case? 290, yeah. So if you're going counterclockwise from the x-axis, you go 90, 180, 270, and then you have to go 20 more degrees to get to it. Anybody have any questions about that? Do you see what I'm talking about? And so this is 98.1 times cosine of 290, 98.1 times the sine of 290. Punch that into your calculator, and it gives you 33.52 negative 92.18. So that's the weight force in this rotated coordinate system. Does it make sense looking at this picture that it has a positive x component and a negative y component? Well, remember that the components of that vector are just the coordinates of the head if you put the tail at the origin like this. So look at that coordinate system. Does it make sense that the coordinates of that point are positive in x and negative in y? You know, just turn your head so it matches up with that coordinate system. You can see this is in the fourth quadrant, so yeah, that makes sense. And so now we can go to Newton's second law. So we have the weight force, 33.52, negative 92.18. Plus 0n is equal to the mass, 10 kilograms, times the acceleration that we're going to put in here is a0. And if we want the we want the acceleration vector, we just want to calculate that a. So we're going to use the x equation. It says 33.52 is equal to 10a. So a is equal to 3.35 meters per second squared. Plug that into the acceleration vector, and you get that the acceleration vector is 3.350. That's in the positive x direction, which is down the ramp. And so you could also think of this as an acceleration down the ramp of 3.35 meters per second squared. So that's how it works, that gravity for this thing on a ramp makes this accelerate down the ramp. Any questions about that? Okay, let me give you one so you can sort of try to wrap your head around this weight thing. The weight thing is really the only tricky, new wrinkle about this. So let's say now there is a ramp this way. Let's say that well, let's do 20 degrees again. And let's just do a cart like this again, but let's change the mass of it and see if that affects the acceleration. So let's make the mass 20 kilograms this time. So this time we're going to use a coordinate system that the y-axis points out. That means that the x-axis points up the ramp. Take a minute and draw the free body diagram. Okay, we're just going to break this up into steps. I'm going to let you do the steps and then I'll do it so you can check and make sure you're thinking about it right. So it really looks a lot like the last one. Everything's just happening at a different angle. There's a weight force down of 20 times 9.81, so that's 196.2. And then there's a pushing force from the ramp, like that. I'll call that N. And now the next step is to figure out the components of the weight force in this rotated coordinate system. So I'm going to draw the coordinate system like this. Draw the weight force like this. That has a magnitude of 196.2. Since this ramp is at 20 degrees, it's 20 degrees from the vector to the negative y-axis, so that's 20 degrees. Okay, so take a minute and see if you can calculate the component. Okay, so what angle are you going to use for cosine and sine here? Is it going to be 250 or 290? 250 in this case, right? Because you start at the x-axis, you don't make it all the way to the negative y-axis, so it's going to be short of 270. And so this time, you're in the third quadrant, so both components should be negative. So this is going to be negative 33.52. No, it's a different weight force, right? Let's see. So we got negative 67.10 and negative 184.37. Anyone get anything different than that? Okay, so now that we have that weight force, write out Newton's second law and see if you can calculate that acceleration vector. Okay, so Newton's second law now. We have the weight force that I calculated here, has components negative 67.10, negative 184.37. And then the normal force, 0n. And that's equal to the mass, 20, times the acceleration, a0. I'll use the x equation, and it says negative 67.10 is equal to 20a. Solve that for a, and you get negative 3.35. And so the acceleration vector, plug this value back into the vector we have here, you get an acceleration vector of negative 3.350 meters per second squared. Or what does that mean in directions? Look at our coordinate system. We got a negative x value, so it's in the negative x direction. So down the ramp with a magnitude of 3.35 meters per second squared. So what we figured out is that with this ramp at 20 degrees like this, no matter what the mass is of that rolling thing, the acceleration is going to be down the ramp with the same magnitude, 3.35. Okay. In practice, it's worth pointing out here that we're doing problems like this without considering the mass of the wheels. And the mass of the wheels would matter. If anybody here is a cyclist, you know that the mass of the wheels on your bike make a difference in how you accelerate and stuff. So since we're assuming that all these wheels have zero mass, it doesn't matter. But if say that these two had the same wheels as each other, and these wheels did have some amount of mass, the heavier thing would accelerate a little faster down the hill, depending, and how much faster would depend on the mass of the wheels compared to the mass of the body. But if we're assuming that these are, basically what we're assuming here is that this is just like sliding down the ramp with zero friction. And that's what we're calculating. Any questions about that problem? Okay, let me do one with friction. So this time, let's say that there's a ramp that makes an angle of 30 degrees. Let's say this has a mass of 2 kilograms. And let's say, remember, with any friction problem, you need to know which direction the thing is sliding. Let's say that motion is going this way at this instant. And let's say that the coefficient of friction for this block is 0.1. So what's the acceleration vector? So like always, I'll start with a free body diagram. I guess first I'll just show the direction of the coordinate system. So y-axis comes out of the surface. X-axis goes up the ramp. A free body diagram. There's a weight force down of 2 times 9.81, so that's 19.62. The only place where the surroundings contact the boundary is at the bottom. And since there's friction here, that happens in 2 parts. There's a pushing force like this. And then there's a friction force opposite the direction of motion. Since motion is down the ramp, friction force is up the ramp like this. And the magnitude of that force is the coefficient times that normal force. So let's think about the components of the weight force. This angle is 30 degrees. So what's the angle I'm going to use for sine and cosine? $240. Yep, exactly. So it's 270, in this case, minus 30. So 196.2 times cosine and sine of 240. So for the x component, that is negative 98.1. For the y component, that's negative 169.91. Oh yeah, so move those decimal points over. Thank you. So 19.6 negative so the total is negative 19.62. And so the x component is negative 9.81. The y component is negative 16.99. Thank you. So now Newton's second law. I'll do that weight force first. Negative 9.81. Negative 16.99. Then the normal force is 0n. Then the friction force, this one you have to put in the right direction. So did I draw this friction force in the positive x or negative x direction? Positive, yep. So this is 0.1 n 0. And then this is all equal to the total mass times the acceleration, which is a0. Notice if I went right to the x equation, this is always true in these friction problems. I have two variables in that x equation, so I couldn't solve it right away. So instead, I'm going to go to the y equation first to get n. So n is equal to positive 16.99. And by the way, if you ever get a negative value for n, something went wrong, and you should go back to the free body diagram. And now we'll go to the x equation. Negative 9.81 plus 0.1 times n. We just figured out that n is equal to 16.99. Is equal to 2a. And so we get that negative 8.11 is equal to 2a. And so a is equal to negative 4.06. Now plug that back into your acceleration vector, which is this thing here. You know, our acceleration is always just a0 for these rolling and sliding problems. So our acceleration vector is negative 4.060 or down the ramp with a magnitude of 4.06 meters per second squared. Any questions about that? So is this object speeding up or slowing down? It's speeding up because the motion tells you the direction of the velocity. In this case that we got that the acceleration and velocity are in the same direction, so that means speeding up. Okay. Let me do one more problem and then we'll end sort of early today. We're pretty far ahead in this class compared to the other class. So this time, let's say we have a ramp going this direction with an angle of 10 degrees compared to the horizontal. And we have two carts. Let's say the front one is 100 kilograms and the back one is 80 kilograms. And they're connected by a cable. And let's say there's a force of 300 newtons trying to pull them up the ramp. Let's say we want to calculate what's the tension in the cable that's holding those two together. In that middle cable. And why would you want to calculate this? I mean, if this was really like a hill that for some reason you had to get these things to go up, you would want to know how strong you had to make that cable between them so that it wouldn't break. Okay, so it's sort of a reasonable engineering type problem. We're going to use a coordinate system oriented like this. And now this is combining two things that we've done. This is a collection of bodies with the same acceleration, and it's also on an incline. So for a collection of bodies with the same acceleration, what's the first thing we isolate? What's our first free body? Both, exactly. Yep. So for the free body diagram, we're going to do the whole system. I'm going to put a little more effort than is necessary here into making it clear what this is, but okay, so there's our free body. And the total weight force is the total mass times 9.81, so that's 180 times 9.81. So 1,765.8 newtons down. Then there's this pulling force that we're given over here on the left. That's 300 newtons. And then there's a pushing force from the surface onto the wheels, and I'll call that N total. Any questions about that free body diagram? To figure out the components of the weight force, we have this weight force vector of 1765.8. And this angle is 10 degrees. So we know the angle we're gonna use for cosine and sine is gonna be either 270 minus 10 or 270 plus 10. So is it gonna be 260 or 280 here? So start at the x-axis, go around, you hit 270 and then have to go 10 degrees farther to get to the vector. So this is gonna be 280. So this is going to be 1765.8 times the cosine of 280 and 1765.8 times the sine of 280. So that gives you 306.63 negative 1738.97. So that's the weight force in the rotated coordinate system. And now I'll go to Newton's second law. So there's the weight force that I just calculated. Then there's the 300 that's in the negative x direction. So that's that's negative 300, 0. And then there's the normal force, that's 0 in total. And all this is equal to the total mass, that was 180, times the acceleration, a0. And we're just doing this to calculate the acceleration. So the x equation says 306.63 minus 300 is equal to 180 times a. And so a is equal to a very small positive acceleration, 0.0368, I guess I'll keep another digit, meters per second squared. And so the acceleration vector is equal to 0.0368 and then 0 for y. Are we done with the problem? I mean, it depends what you're being asked for. I mean, if the problem could have asked for the acceleration, but instead it asked for the tension in that cable. So now we're going to have to isolate one body or the other one. And it's sort of cool to note that no matter which one of these two you isolated, even though the free body diagrams would look totally different, the equations would look totally different, you'd get the exact same answer either way. Okay, so you can do either one. I guess I'll isolate the 80 kilogram, but it doesn't matter which one you do. Okay, so the free body diagram looks like this. The weight force is 80 times 9.81. So that's 784.8. $780, is that right? Yeah. Where else are the surroundings making contact with the boundary of the 80 kilogram cart? Cable, yep. So the rule says that's parallel to the cable away from the body, and that's T. And all we're trying to find is that T. And then there's one other place where the surroundings contact the boundary. The normal force, yep. And I'll call that N80 just to be clear that that's different than the N total. The weight force, we're going to use the same angle we did before. So that's 784.8 times the cosine of 280. And then 784.8 times the sine of 280. So that is positive 136.28, negative 772.88. And now Newton's second law. So we have 136.28, negative 772.88. That T is in the negative x direction, if you look at our coordinate system. So this is negative t, 0. The normal force is 0 and 80. And all this is equal to the mass of 80 kilograms times the acceleration, which we figured out in the first part. So that's 0.0368. And then 0 for y. The x equation says 136.28 minus t is equal to 80 times 0.0368. And so t is equal to 133.34 newtons. In this one, I just asked you for the tension in the cable. I didn't ask for a force vector. If I had asked you for like the vector, the force vector that this cable applied to one body or the other, then you'd have another step of plugging this into a vector. But this, if I ask for the tension, this is the answer, just a number. And tensions, just like normal forces, always have to be positive. So if you ever calculate a tension and you get a negative number, if that t variable is ever a negative number, something went wrong. Okay, any questions about those? All right, that's all. So enjoy the long weekend, and I'll put a problem or two up for you to do.